David Reed, who I think a lot of you have met over the last few years, given his time here in our department. But for those who don't know, David Reed is a ecosystem scientist, hydrologist, ecologist, whatever, who got his PhD at the University of Wyoming, the atmospheric science program, right? And has been working for many years on a variety of ecosystems, from western forests to the Midwest, and as we'll hear about today, some of these agricultural systems. He joined University of Wisconsin as an NSF atmospheric science postdoctoral fellow in 2015 or so.
Sounds right.
Yeah, and was part of our lab, my lab, and not too surprisingly, given that the word flux tower is in the title of the talk. And we did some cool stuff. David set up the eddy covariance flux tower that you might have noticed if you've ever walked out to the end of Picnic Point, along with our lab manager, John Tom. And so if you've ever noticed, there's a sonic anemometer sitting out there. There's actually, we're seeing how the lake evolves in time, and aquatic limnology is just one of many various ecosystems and systems David has looked at in terms of surface atmosphere fluxes. So today, David is now a research associate at Michigan State, working with Professor Ji-Kwan Chen, who is also another micrometeorologist, who has set up a very large number of eddy covariance flux towers. We will soon try to beat that number next summer, but in the short run, we're going to hear a little bit about what you can do and what you can learn about the landscape in terms of its surface flux and its evolution in time using a variety of new statistical techniques. And so, David.
Thank you. Yeah, as Ankur said, I'm atmospheric scientist by background, but I have done quite a bit of kind of applied ecology work. Half of this work, give or take, has been done by an absolutely wonderful undergraduate student that I'm working with, so I want to stop and give her credit. Right now, we're kind of focusing on carbon fluxes, and so the units on some of the figures will be, net ecosystem exchange. However, I'm going to stop and point out now and in a couple slides that, surface fluxes are surface fluxes. We've started with carbon cycling analysis. We're going to do heat fluxes from the land surface. All of it eventually ends up in the atmosphere. So hopefully you guys aren't just showing up because your advisor told you to. It might actually have to do something with the atmosphere going forward. So this is an idea that I've wanted to do for a little while. One of the nice things about being a postdoc, other than all of a sudden like people listen to you and you get paid a little bit more, you can actually start to work on some of your own ideas kind of independently, sort of independently. So again, I've had this idea of how can we take information from roughly 1 square kilometer of the Earth's surface and like scale it. Does it matter? A little bit outside of the tower footprint. We started kind of working on similar questions, kind of as a lab-wide thought experiment when I was here working with Ankur's group. We got pretty far. No one really took that project and led it, so I think there's still probably a folder of some code sitting around that could be a good paper. But when I showed up at Michigan State University, I kind of stumbled upon a great data set that I could take this idea and really test it. Michigan State University has one of the first long-term ecological research sites. This is one of several maps that they have. It's agriculture. They have a lot of different fields doing a lot of different research there. Back in 2009, I think, give or take, this red box here is the map of Kellogg Biological Station that was, for the history nerds, was donated by the Kellogg family. So everything in that part of the state of Michigan is named after the Kellogg family. But anyway, MSU came across another couple chunks of land, and they were expanding. And so my advisor at the time wasn't even at MSU yet. Decided to put up 7 different flux sites. It's a really cool experiment. They have these 2 different plots of land, had different land use history, so it's really great ecological data. And then they have different land cover types since they were all kind of standardized. But what's really cool is we have 7 flux sites that are all spatially very close together, which is pretty unique. And then, as part of the project that my advisor got funding for and brought me on, we put in 5 more flux sites, all kind of in the same watershed, plus then one on campus, which is that kind of dot up here to the northeast. I like to say that this is, right now, for another couple months, the highest density cluster of flux sites, I think, anywhere in the world, which allows us to really answer some of the same questions, but in a kind of a novel way. And then, because Ankur loves to share data, I pulled in some of his data sites as well, which will help populate a figure that I will show in a couple minutes. So, to set the stage a little bit, again, this is an idea of wanting to have time to explore for a little while. Here we have a picture of a flux site. It's kind of a cool one because we can crank it up and crank it down underneath an irrigation system that goes through this cornfield here. It's measuring net gas exchange with the land surface in the lower atmosphere. We can back out and calculate net carbon, and then we can use some, at this point in time, pretty safe assumptions and estimate gross photosynthesis and ecosystem respiration underneath this tower, so in the cornfield. And then we can also measure heat exchange from the land surface in the lower atmosphere. These are kind of a pain to set up. It's a good chunk of money. It just takes time, as Ankur would love to tell you. Setting up 17 of these is not quite trivial. So what most people do is kind of spread them out over the landscape, trying to get representative land cover types. At this particular site, just down the road, we have the same landowners. We have a soy field. Again, people spread them out. But they produce a ton of data. We can quantify net carbon or net heat exchange over annual timescales. We calculate fluxes every 30 minutes, and so we can get wonderful kind of daily timescale and hourly timescale process level information about the ecosystem. Again, roughly a square kilometer, give or take wind speed and turbulence characteristics underneath each of these sites. So we can pull a ton of data from this cornfield here in the middle of Michigan and do a lot of work to understand why it's behaving the way it's behaving. However, if we were to set up a hypothetical second sensor, 5-10 feet away, the idea that I have as I'm sitting out here in this cornfield setting this site up is it's going to essentially record the same exact information, the same signal, right? We move the footprint over 5 feet. It's, 12 rows of corn or whatever. Corn, to me, I'm not quite a plant biologist. I'm sure somebody here on campus would disagree with me, but a corn stalk is a corn stalk is a corn stalk. So you move the footprint over a couple feet, and I think it's going to be, I've offset them just to highlight, it's the same exact data. I think it would be exactly the same data collected if we move the site 5 feet this way or 5 feet that way. So if we move this hypothetical second site to the other edge of the cornfield, I think it would still basically record corn data. If we move it down the road or across the street, here is just a Google map. That was that site, and we have, again, this soybean field just down the road, 2.5 or so miles away. At some point in time, I think the coherence of the signal is going to start to break down. Right, so if you move a second site all the way into Kansas, it might still be recording corn, but I don't think it's going to be the exact same data set. Whereas if you move the tower 10 feet away from the actual tower, you could basically just copy and paste the data over and have a second site there. So that's what, again, I've been thinking about and wanting to answer a host of questions for a couple years now. And to break it down, kind of what I'm working on, really what my undergraduate students are working on and what I'm working on. I want to use this really high density network of flux sites to try to quantify a relationship between signal coherence between sites. And then, if that's possible, and spoiler alert, it probably will be, is there some distance that we can look at and say, okay, if we move a flux site 5 feet over, it's probably the same, right? If we move it across the field, it's probably the same data. If we move it across the county, at some level, it's not going to be the same data. And so is there some distance that I feel comfortable saying, it's probably the same if we put a second observation point in on the land surface? As we're doing that, we can actually quantify across the Midwest modes of variability and looking to see if all of these land surfaces are basically behaving the same way. Then, at the same time, I basically want to take those same set of questions and invert them. And so, if we believe that we can move one observation point 10 feet away into the same cornfield and it's probably the same data, can I model that, right? Well, yeah. In that case, I can just, again, copy and paste the observations into a new file, and there's probably 99% good enough the observations from a second site. And let me back up really quickly, or mention really quickly, in the anti-covariance community, there's lots of error. Roughly speaking, I like to think, we can make an observation plus or minus 20%. So at some point, there'll be some rough error assessment in there of like plus or minus 20%. So if we can model or simulate fluxes in the same cornfield within 20%, it's probably just as good as putting up a whole other flux site and getting a set of instruments that are going to have its own calibration sensor issues and drifts. And then kind of the work I'm ending on today is how much of the landscape can we actually extrapolate out to. And I think that this will have some cool implications when we have a discrete number of observations across the landscape, and that's kind of sort of it. Like, how do you actually connect the dots in the landscape level ecology or landscape level surface fluxes, and answer bigger picture questions rather than what's happening with the heat fluxes in one cornfield in Michigan? Can we answer a little bit bigger picture questions than just that one cornfield? At any point in time, feel free to stop, ask questions. It makes sense to me. I'm not going to make the assumption that your brain works the same way mine brain. So
I will ask a question. So the emphasis so far has been primarily on coherence as a function of distance.
Yes.
Which is what you're plotting there kind of schematically. How much do you also have to pay attention to other variations in the environment that are nearby your station? In other words, if you're 100 meters downwind of a forest or something like that, you may get different results than if you're 100 meters downwind of a wheat field or something like that. So does that come into play, and do you have to disentangle all of that?
The short answer is yes. The medium answer is we've done all that by first rescaling all the data. So instead of saying the heat flux is 70 here in a cornfield and 50 over in a forest, we've rescaled all the fluxes per site to go from 0 to 1. So then all of a sudden, the cornfield and the forest are at least in the same orders of magnitude. Now the rest of it is there differences, between what's upwind or the same exact question I think coming from an ecologist was, have you looked at variation in soil? Yeah, and that goes all the way back to my idea that, within one cornfield, sure there might be different things upwind, but it's probably still corn data within 10%, uncertainty. At some level, it will matter, and in Michigan, it's the closer you are to the lake, the very different climate you experienced. And so I do think that stuff matters. Right now, I'm not directly untangling it, but I know that does matter. And so I want to see, first, if there's a relationship kind of across the sites, and then I'm going to try to disentangle it. Does that make sense?
Yeah, you're basically trying to pick sites for right now where that's not a factor, where it's fairly homogeneous.
Right.
Yeah.
Yep.
Thanks.
Again, to kind of step everybody through this, because it makes sense to me. If we take two sites that are close together in the same cornfield or maybe across the street, I would expect them to be pretty highly coherent in time. As we go farther away, at some point in time, they're not going to be coherent. I'm not sure, at least a couple months ago, I'm not sure what this relationship would look like, as I do now. But I'm also really interested in looking at kind of a physical distance that I can pick off that I think the coherence would be high, assuming everything else, what's upwind, the microclimate, the soils are going to be similar. But can we find 2 points in the landscape close enough that I have some degree of confidence that they're going to be behaving relatively similar? So that's exactly what. Oh, yeah.
Sorry, one more question.
Yeah.
So coherence, are you defining that on a certain time scale? Because I would imagine that your coherence versus distance tails off much more slowly for low frequency variations. In the limit, you go to seasonal variations, whereas if you're looking at the ultra high frequency, it's going to be very short. So do you pick the time scale over which you're making that?
Yes. Right now, we are looking at 1 month, mostly because that's where all of the sites were up and running as I was kind of building new sites in this network. We are going to expand this in my preferred method of working with undergrads is to not overwhelm them. And so I've started with Geraldine and say, can we work with 1 month? And then once we understand what's going on, we can kind of come back and add in the, ideally I'd like to get summer all the way through winter, that like fall transition. And yeah, in a couple more slides, I do have actual spectral information that shows, I think, it's essentially showing that kind of late summer shift into fall that all ecosystems, all land cover types are doing at that point in time, if that makes sense. Yeah, so right now, that's a very good question. Right now, it's just 1 month. I'm hoping to add in more data and kind of expand the frequencies that we can look at. So this is, again, what I don't think anybody else right now, Ankur will be able to recreate this figure in a year or so. But right now, we have all of these sites that are very close together, and so we've just went and made the comparison between one site and all the rest of them spatially, and then just did a temporal coherence calculation, and sure enough, to me, there is some type of relationship there. I want to pause really quickly. We have in that network, 2 of the sites are urban sites. When we add in those sites, there's this big mess of sites down here. That's all the 2 urban sites paired to all the other sites. So when we first made this plot, I was like, oh, it's not quite what I expected. And we looked and saw, well, there's clearly a cluster of low coherent sites to the urban sites to all the terrestrial sites. So I think that in itself, even though I'm not showing that data, is a cool finding that terrestrial sites kind of sort of follow what I was hoping to see, but the urban sites compared to terrestrial sites are really doing their own thing. So right now, I spent 30 seconds to put a linear fit through there. I don't think this is the best way of doing it. It's not a great fit, but again, this is what I'm trying to work towards AGU, so don't judge me now. I'm going to have something better in about a month. But remember, I think I said this, that this is net exchange of CO2. So this is the combination of photosynthetic uptake of carbon in the landscape and the ecosystem release of carbon. It's a pretty complicated signal because it's going in both directions, positive, negative. It's all rescaled, but it's complicated. I think what we want to start doing next week is look at the same temporal correlation between all these sites for a little bit more simple, just the photosynthesis and just the respiration signal. And I think it would start to essentially flatten out this line a little bit, as the idea is that net carbon exchange may be a little bit more complicated across the landscape. Photosynthesis is going to be a little bit more simple spatially across the landscape. When the sun comes up, for the most part, plants are going to do photosynthesis. And then if we start to look at surface heat fluxes, I think it's going to flatten out this line a little bit more because, again, when the sun comes up, there might be different rates of photosynthesis going on, but heat flux is heat flux is heat flux, I think, across the landscape. So essentially what that will do, I think the next slide, so we're looking at what distance would a reasonable person believe data from one site could be connected to a second site. right? Right now, it's roughly speaking, 20 kilometers is kind of one cutoff, and then somewhere a little bit closer right now, we've just picked a number at about 5 kilometers for this tight, more tight grouping of higher correlation up here. But again, I think if we look at heat fluxes, I think it might be a flatter line and it might push out this distance a little bit more. Keep that in the back of your mind as I kind of get to my last couple slides showing what spatial scales we're talking about. But yeah.
Definition of a reasonable person.
That's a good question. That's something I've thought a lot about. We're again kind of going back to 20% of observations plus or minus. Here we have one pairing of sites. Off the top of my head, I forget which one this is, but they're essentially the same exact data, even though they're a couple kilometers apart. At what point is good enough? So what I'm not trying to, and this is I think the next point I'm going to try to make. No, it's not. So I'm going to go back really quickly. I'll make this point again in a couple more slides. But what I'm trying to do here is not necessarily predict fluxes at 3 o'clock on a Wednesday afternoon in a cornfield across the street from where I have a cornfield site. What I'm trying to do here is predict annual or maybe monthly sum or mean fluxes across the street from my site. So to me, I don't think that I need 100%, this is exactly the same data in order to feel confident, in 100% the same data in actual measurements in order to feel confident that I could extrapolate that, across the street. Does that make sense?
I think so. I think another way to flip the question is to think about, depending on the scientific question being asked, right, that focal point may be different.
Right.
Like if it matters that a 20 watt per square meter difference influences some circulation, then that line might be different. It'd be interesting to come up with some sort of relationship between expected uncertainty and distance, right?
Yeah, it does. It does to me at least. Okay. So again, we can kind of look at all this data as it's varying in time and look to see if there is any type of variability modes that are common with all these data sites. Again, we know right now we're doing daily data, but if we looked at hourly data, we know when the sun comes up, all the sites are going to be doing photosynthesis in the morning, right? We know that there's going to be some type of variation temporally that's common across all the sites, but we can quantify that. So to do that, we've used the same exact methods that a lot of climate scientists use, in this case, in the North Atlantic Oscillation, to kind of quantify variability in space and time. And so, again, here's the map that we're working with, kind of a large cluster of data in the southwest of Michigan and a little bit in the northern Wisconsin. And this is essentially time series of principal component analysis of net carbon exchange information. So there's wiggles, great, the code works. What does that really mean when we look at what the variability modes are? When this graph was produced, it's like fantastic, this looks good. The sites in general are varying coherently across the Midwest. And to interpret that, this is the net carbon cycling, and now we have air temperature here. And it's sure to me, by eye, right now, we need to again kind of continue this work, but it looks like air temperature across the Midwest is varying similarly to net carbon cycling across the Midwest, which is kind of sort of what I would expect, right? On warm days, photosynthesis is going to be a little bit higher. On cool days, photosynthesis might be a little bit lower. The initial question that we were working on here is, could we see essentially cold fronts and warm fronts moving across the Midwest? Because I think that, when the temperature drops by 20 degrees, in this case late summer, plants will respond differently, and that's probably noticeable, not just at one site, but across the whole array of sites. So I'm still working on this. Well, wait, my undergrad's still working on this. We're still working on how best to actually connect the dots in a way that makes sense. But it's exciting to me that, again, we see all these sites essentially wiggling in a common mode across the Midwest. And then again, we compute in a spectral sense that same mode here. And so again, this is just over a month, 5 weeks I think of data or something like that. But we see a lot of the variability at the lower frequencies. And I think again, this is showing the transition of late summer into early fall with net carbon cycling and also air temperature across the Midwest. If we were to redo this using hourly data, my assumption is there'd be a massive spike at the 1 day period, right? And that's just the sun going up and the sun going down. So it's exciting to me that there's a lot of information, a lot of very common modes of variability at lower frequencies. So the kind of the work that I'm doing, which is again is inverting, to me, it's inverting a lot of these questions on their head. Can we take one site and use it to simulate data from another site? So we have these wonderful paired data sets that go back like 8 years. They're, I think, 2.5 or so kilometers on average away from each other. And we've done a lot of the same computational work in our field. We've just done it at one site and we've called it gap filling. So what I mean by that is we have all of the surface flux information that we primarily care about. And when a sensor goes offline for a day or an hour, there's a gap in that time series. We use all of the ancillary data, the environmental data, air temperature, soil moisture, vapor pressure deficit, all the good stuff there, coupled with a lot of assumptions or theoretical work of what the relationship is between air temperature and soil temperature and respiration, right? When it's warmer out, the soils and plants will respond more. We can use all of that relationship between different types of data, use that to gap fill the surface flux data, what we have been doing for a decade or so now. We've also used artificial neural networks to do the same exact thing, which is instead of having, I expect there to be an exponential relationship between environmental temperature and respiration, we let the data kind of sort of decide what that relationship is in order to do the best job gap filling the surface flux information as we can. And in fact, you know, a decade ago, there's a paper that shows all these different techniques, and one of the findings was artificial neural networks are basically, you know, a couple % better than other techniques. But the idea is we can use some type of modeling to go from the environmental data to fixing our gappy time series of the surface fluxes. Right? Now, what I want to do is take that same exact idea and bring in a second site. And they're paired sites, so I don't have any reason, for the most part, to believe that the relationship between ecosystem respiration and temperature should be really different. It's a cornfield and it's just 2 kilometers away. So what I'm trying to do here is take all of the relationships between, you know, the environmental observations and surface fluxes at one site, combined with the same exact air temperature, soil moisture, radiation, precipitation, all the other environmental data just down the road at the second site in order to model the surface fluxes at that second site. And again, I'm going to do this either at the daily time scale, so for today, or the hourly time scale for 3:30 on a Wednesday. But then I don't quite think that that's what my question is. Like, can I do it for 1 hour on a Wednesday? Sure. I want to aggregate these surface fluxes for monthly and annual timescales, kind of compare to a rough, is it within 20% benchmark of the surface fluxes. And what's amazing about this data set that I kind of stumbled into is that we do have a second site out there, right? We have 8 years of corn data at this second site, or 8 years of switchgrass at the paired switchgrass sites. So we can simulate all of this and actually compare to real data to see if it's possible. And that's exactly what I mean here. It's a paired site design, so we can kind of go both ways and use data from one site to model the other site, use data from the other site to model the first site, and go back and forth. I'll fully admit the next couple slides I don't feel are showing the data super well, but this is kind of raw output from the artificial neural network, where we first take all of these time series and first train the artificial network for 3 years, and I think it does a pretty good job. There's an emerging body of literature in the kind of eddy covariance ecology community that shows that individual peak days can have an outsized effect on annual summation fluxes. And so I think the artificial neural network definitely nails the daily and annual timescales. It's not quite getting those peak days. So it's not a perfect model, but I think it's going to be fine for my purposes. Here, then we have 3 years of validation data, where obviously the model struggles a little bit to get some of those peak days. And we have 2 years to test the model, and overall, I think it's a pretty good fit for what I'm there we go. I think it's a pretty good fit for what I'm trying to do, which is, again, even though I'm modeling daily data, I'm going to aggregate it to annual or maybe even monthly timescales. So when we take, this is the one of the 2 switchgrass sites. When we plot everything out, it's a little bit messy, and again, I'm trying to figure out the best way of displaying this in a coherent way. But we have the net carbon cycling observations, and then the modeled carbon cycle information in the black. We have ecosystem respiration in red, and then the gross primary productivity of photosynthesis in green. It's by and large getting the seasonal cycles correct. I think that was not surprising after we saw how good the model fits were from just a regression point of view. There's definitely a lot of interesting stuff in there, but we're going to work with the annual timescale right now. The same exact data, just showing annually what's going on. And I think right now it's working well. But what I'm really interested in looking at kind of is the percent error, right? Is how far away the model is from the observation. Again, knowing that plus or minus 20% is kind of sort of my first benchmark of, is this even close? Are we in the right ballpark? At an annual time scale, there are definitely some years where we're pretty far out, but I think most of the data is not bad. So we can say, again, 3 kilometers away, we might be able to fake or model a whole bunch of surface fluxes, and at the annual time scale, maybe get the balance correct. Forward. Here we go. Now if we add the second site, right, because it's paired sites, so we can use one to model the other, use the other to model the first one, we basically just double the data that we have. The NEE, one of the 2 sites is kind of sort of wrong, and I think that that's 2 parts. 1, because that's more complicated of a signal, and 2, it's closer to 0, because you have photosynthesis going one way and respiration going the other. So even though the error themselves is small, when you're close to 0, the percent error kind of balloons a little bit. But to me, it's pretty encouraging that the photosynthesis and respiration fluxes are pretty close to being what I would call good enough to model. Now if we go from daily observations of the surface fluxes to hourly observations of the surface fluxes, so basically throw in a factor of 48 half-hourly data points a day, expand everything by that. we see that it's super complicated, and I'm not trying to say that this is a good way of showing the data. It's just what I worked on yesterday. We see that the predictive power doesn't really change. It gets slightly better. Some of the other sites got worse. The corn sites, I think, got better. So going from daily data to 30-minute surface flux data doesn't necessarily seem to improve our ability to estimate annual fluxes at these sites. So what I'm trying to wrap this up at, we have this 7th site that's completely untouched, not managed. It's basically just a native grassland. What I'd like to do next is, can we use these other more managed sites and predict basically an unknown land surface type, right? Can we go back and say, we have data from a corn, can we use that to predict information on a grassland? In the future, I'd like to say, can we use information from a corn site and predict information at a forest site, right? There's no real reason why we wouldn't be able to do that computationally. I'm not sure yet if it makes sense ecologically, but that's a conversation for me to have with ecologists, I think. And again, we have this, I think, we're starting to quantify this relationship between intersite distance and temporal coherence. And I think if we pick off, again, 5 kilometers and 20 kilometers right now, and well, we can look at all of our sites and we can say, well, we might be able to extrapolate our information out into the land surface beyond our discrete sampling points. At the whole Midwest scale, it's not super exciting to me, but if we zoom into Michigan, all of a sudden, 1 or 2 sites, we have a pretty tight cluster of sites, but you could have 1 or 2 sites that essentially cover the entire county. And then we can go from understanding exactly what's happening at one individual cornfield very well to maybe having a good idea of what's happening across maybe cornfields in the entire county, maybe corn and soy and wheat fields across the entire county, maybe even we can go from 1 or 2 cornfields in one county to understanding all terrestrial ecosystems in a county. It's a little bit of a harebrained idea, but I think, to me, it seems to be working fairly well. So again, I really want to say that my undergrad that I've been working with has done roughly half of this work, probably the better half of this work. Both of us are attending AGU. She'll be presenting her work on Wednesday. If you have a bunch of questions for her, feel free to ask me now, or talk to her at AGU. And I've talked to a couple faculty members, but I'm actively encouraging her to think about graduate school positions, even though she won't be applying for a year. So, thanks, and I'd be happy to take any questions or concerns or comments that you guys have. Yes.
So I'd like to go back to where you use the neural network with the 3 inputs.
Yes.
And of course, what you're doing is you're using 3 different kinds of information to all kind of throw it in the hopper and generate a prediction of what comes out.
Yes.
And the interesting question to me would be what happens when you then look at the individual contributions of each to the overall skill. I would expect that the upper left one is the least direct and therefore that provides the least additional information relative to the local environmental observations and the remote surface fluxes. But you could easily basically train a neural network on one at a time and see which one does the best job by itself, and then how much information is added as you throw the next one. Have you already looked at that yet?
That's on my to-do list.
Okay.
I started with the idea of like, I have it all, I'm just gonna throw the kitchen sink at it.
Mm-hmm.
And I think, you know, air temperature and soil temperature are right now both tossed in there. I'm not sure if both are needed to get some estimate of fluxes that then aggregated up.
Because, for example, I would think that if you have the local temperatures, the remote ones probably don't add much value, right?
Right. Yeah.
So you might find that one becomes
Redundant.
So,
Yes.
and if anything, you can simplify the model some.
Yep.
It's just a thought.
I don't think I understand this stuff as well as you guys obviously do, but is that a way where you could get rid of the reasonable person part of the problem and say which of the weakest link, if it falls below a threshold of contribution, that's my distance between site 1 and site 2? Is that another way to approach that problem?
Yes,
Okay.
it is.
So maybe the question is, what threshold would a reasonable person choose?
Yeah, but can't you, yeah, and you could avoid that with just thinking about it from your voluminous data set statistical perspective probably, right? Just say,
Right.
what am I going to call my reasonable threshold?
Right.
And then you can defend that more easily than your definition of a reasonable person, especially in our country.
Yeah.
So your sites are managed. Are they roughly planted and harvested at the same time? I'm trying to think about like where that might fall apart, right?
Yes.
In terms of the scaling issue.
The corn, the switchgrass is managed as a biofuel crop. So the switchgrass and the corn are harvested, planted and harvested every year. The prairie is just left as a prairie. There is a lot to tease apart there in terms of the actual management side of it.
Yeah. Well, I was thinking too, like talk about this idea of scaling large regions, right? There's going to be variance in some of those factors that would have strong strong peaks and spectral signatures that you cannot pick up as coherent.
Right.
But you could put it in as a covariant in a neural network, right? Like
Yes.
the state, for example.
Yes. Or if you have, a site that is managed and a site that's not managed, the network should be able to pick one or the other as you're extrapolating out to a point in between, depending on if it is managed or not. Right? Because to me, I think it's all about the relationship that the neural network builds within all the variables that I give it. There's no reason why it shouldn't be able to do that itself. If you give it the land management, this is managed or not, I think might be enough. Yeah.
So I'd like to come back to kind of my early question about the time scale that you're looking at. I realize now you're dealing with a time set, time data set, which you probably go down hourly, right? Minimum,
Mm-hmm.
and then monthly is the maximum or something like that?
For some of the first half of the work, and then the artificial neural network was 8 years.
Okay,
Yeah.
8 years, okay.
Two different data sets.
Okay,
Or-
but
yeah.
regardless, there's a Fourier technique, the calculation of co-spectra,
Mhm.
where you have two time series and you look at the co-spectra of those, and they basically reveal where in the time scale, where in frequency do coherences or correlations occur, and maybe anti-correlations in some cases. That would again maybe provide a tool for saying, well, at these low frequencies, the coherence between our two remote data sets is very high, and it falls off as you get to finer frequencies because they don't communicate over those distances as well.
Right. And correct me if I'm wrong, you can only put basically two variables into that, right?
Well, you can do it pairwise, I guess.
Yeah.
So you can get a co-spectrum for every pair of variables.
Okay.
But
So the strength, I think, of this technique is that you essentially put all the spatial data in that you want, and then it's retaining that spatial information. So I'm just giving it our entire array, and it's doing the similar work in space for me, as opposed to just one pair at a time.
yeah, but you're looking in space for a specific averaging period or something like that, right?
Yes,
Yeah, and if you change that averaging period, your results may be different.
correct.
Yeah.
Yes. Yes.
I'm not super familiar with those neural networks, but do they account for temporal autocorrelation? Because I expect, if the temperature is high one day, it's probably very likely to be high the next day, and probably in the region with, I don't know what you were shown, it will be too, so there's a higher likelihood that it will have like an uptake of CO2. Will this, I don't know, is that model accounting for it?
Yeah, it should be. It's not. Yeah, it builds the relationships between the variables, and so I don't. Sorry, I'm kind of blanking on what the terminology is, but it's taking the time series nature of this into account as the relationships into account as well. There's a certain term I'm trying to think of, and it's not coming to mind.
So you call it the temporal autocorrelation?
Yes, Yes. Yeah. So it should account for that, buried within its, the neural network connection itself, yes.
Are you trying to predict the magnitude of the fluxes too, or more the overall?
Yeah, more of the, it is computing the magnitude of the fluxes, but I'm more interested in the signal within the time series itself. Yeah. The delays within the neural network, that's the term I'm thinking of. So you can account for delays between data points. So instead of using today's air temperature, it can look at the last 2 days worth of air temperatures to build a better relationship between air temperature and something else, if that makes sense. So yeah, you can directly specify the number of delays that it will look backwards in time to build that. And I'm still learning a lot about neural networks. There's about a bajillion different types of networks that you can build. And so this one is not a forecasting into the future. This is just taking time series data, looking backwards a set number of data points, building a predictive model for that data point, and then moving forward using the next set of inputs, if that makes sense. So it's not trying to take 8 years of data and then predict what next year, 2019 data is going to look like. Yeah, there's a lot of, it's been a fun learning experience of like, what can you actually do with some reasonable assumptions and limitations with artificial neural networks? And the answer is a lot, because there's different ways of setting them all up, if that makes sense. But yes, to answer your question in a very roundabout way, we can look backwards in time, a specified number of time steps, and pull in information to address that autocorrelation issue. Yeah. Any other questions?
Thank you.
All right.